Welcome to the F+L Webcast. My name is Vicky Denton, and I'm your host. Our guest today is Robert Kennedy. He's the co-founder of Eternal Upcycling. Welcome to F+L Webcast, Robert.
Thank you. Happy to be here.
So, Robert, tell us about yourself.
I am a chemist and catalyst manufacturer. I got my PhD from Northwestern University in Chicago and did a postdoc at Argonne National Laboratory, where I invented a technology with Max Delfero, Ali Erdemir, and my co-founder Ryan Hackler to take plastic waste, polyethylene and polypropylene, and break it down into lubricant oils and waxes. Back in 2022, Ryan and I started a company, Eternal Upcycling, to take that technology out of argon and try to scale it up into a commercializable process to make high-grade base oils out of plastic waste.
So that was a big step for both you and Ryan. Tell us what kind of thought process went into, do I really want to dedicate X amount of time, part of my life, doing this?
Well, it was really two things, and one of them was really the results we were getting back from Ali on the base oils that we were making from the plastic waste, and just how well they performed against Group 3 and PAO base oils. And along with that, just the cost estimates we were getting from the modeling, just how cost effective it was to actually use plastic waste as a feedstock instead of crude oil. And the other thing was really just looking around at the technologies that were being developed in national labs and universities around the United States and realizing that if we wanted to see this technology move beyond the lab, we had to be the ones to do it. And so we took the plunge, stepped out of academia, and jumped into the startup game.
Let's go back a little bit to some of the things that you mentioned. So number one, Ali was your, how would you say it, at Argonne National Lab at the time. He was one of the key scientists. What's Ali? Everyone in the tribology field, by the way, knows Ali Erdemir. But for those people in Asia who may not be so familiar with him, tell us what Ali's role is at Argonne.
Well, at the time, Ali was the lead of the tribology research group at Argonne National Laboratory. So he ran the whole program of developing advanced lubricants and studying very intense wear processes, wind turbines, electrified systems, solid lubricants. And so he was the person to go to at Argonne for lubricants.
I think Ali retired from Argonne, right? He's a really world famous scientist. And he's actually teaching right now, if I'm not mistaken, at Texas A&M. He's still basically very active in the field of tribology. So he was mentoring, encouraging you. Now, second thing is, not a lot of people are really aware of what base oils do and what PAO, how PAO fits in the entire base oil scheme. So maybe let's start from the beginning. How did you come across this field of base oil? Because base oil obviously is one of the components in making a liquid lubricant. And then why PAO, which is one of the synthetic base stocks available?
Like, I'm a inorganic chemist. My background is in making solid state materials and catalysts. And it was kind of eye-opening, just the whole world of tribology. And we had kind of set out to be trying to make fuels, feedstocks for making new plastics. And what we were getting out were these waxes and oils. And really, we didn't know what to do with them. And that's why we turned to Ali to say, what are these things? What are they good for? How good are they? And the it's kind of amazing just how important base oils are for making the economy turn. Everything has to move, and you need base oils to do it. In terms of PAO, um, well, so one of the interesting things about going from polyethylene ethylene to polyethylene back down to a base oil is you're ending up with a very highly paraffinic product, something that is entirely just carbon branching. And that ends up giving you structural pieces that look very similar to polyalpha olefins, which are also effectively very small pieces of polymers. So it's sort of, there's a lot of structural similarity when you get down to it. You're either coming up to the structure of a polyalpha olefin, or in our case, we're breaking polymers down to about the structure of PAOs.
Yeah, because it's interesting, right? You started with waste plastics, um, or your feedstock is waste plastic, not new plastic. And there's so much waste plastics around, um, and we're trying to figure out what to do with them. And a lot of people are actually, for example, looking at pyrolysis oil, making pyrolysis oil out of waste plastics. But you decided to make PAO out of it. What's the difference between um, producing pyrolysis oil versus producing base oil, specifically PAO?
Yeah, so we're using a different chemical reaction. It's called hydrogenolysis, but I guess you could kind of call it mild hydrocracking. We're using a metal catalyst and hydrogen to break down the plastic at low temperatures, and that gives us a lot more selectivity about the output. So pyrolysis, you're not just going to get alkanes, so your waxes and your base oils or your fuel or diesel range products. You're also going to get a lot of aromatics, a lot of unsaturates that for some applications are very useful, but for other applications, they're things that you need to scrub out, remove to make that feedstock useful, and that adds to the cost of using that feedstock. Um, so we're getting a much higher purity feedstock right out the gate, and it's also a lot more valuable hydrocarbon range that we're making. Fuel range, naphtha range products don't sell for nearly as much as base oil range. So it's also for all the time and energy you're putting in to break down the plastic, what can you get paid for the product you're making?
Yeah, so traditionally, how is PAO made from a chemical, from a typical chemical plant? What are the
Yes.
feedstocks? What are the processes that's involved? How energy intensive is it compared to your process?
Yeah. Polyalpha olefins, the kind of the name tells you how it's made. So it poly multiple, and then alpha olefin. So an olefin is a long chain with a double bond at the end. And so alpha olefin, it's at the end. And then a polyalpha olefin is you take two, three, four, six of those, and you react them all together to make one big molecule. And depending on how many you string together, that changes the viscosity of the base oil you're making. That's very energy intensive. I think the ballparks I've seen is that the carbon footprint of a PAO is around cradle to gate. So from starting to make it to the base oil going to a lubricant manufacturer is about 2 kilograms of CO2 equivalents per kilogram of base oil. And we would expect that our products would be about a quarter of that, so around half a kilo of CO2 emissions per kilo of base oil.
And that would be, Robert, using also traditional sources of energy, right?
Yeah.
Uh, Not using renewable energy, for example. Um, so obviously, just the carbon footprint that you can produce from waste plastics, um, a lot of that is attributable to the fact that you're using waste plastics, or is it attributable to your process?
Frankly, that's just the process savings of using a highly paraffinic feedstock and just having to break it down a little bit. Um, Frankly, we are still need to factor in how much more savings there is from the plastic waste being diverted. So there's the potential that if you account for that as well, we might even have a carbon negative base oil.
What kind of waste plastics can you use for this for your technology?
Yeah, so I mean, it's kind of a short list and it's kind of a long list. So we can use low and high density polyethylene and polypropylene. And so that's only three out of the seven plastic numbers, but all told, polyethylene and polypropylene make up more than 60% of the plastic that's thrown away every year. That is your water bottles, that's bags, that's cling film, pallet wrap, yogurt tubs, milk jugs. And really, what we're looking toward is using feedstocks that are not readily mechanically recycled today. So that's feedstocks that are highly pigmented, films, um, rigids. So basically, things that aren't just food containers, but sort of bigger things like children's toys, um, or like pieces of household appliances that make up a sort of large missing piece of all of the plastic that gets thrown away every year.
Do waste collectors actually are they able to segregate all these different kinds of plastics?
Not yet. So some of them they can and would if there's a market. So films is definitely an area where I think we're going to see a big growth in film and bag collection in the next 5 years. In the last 5 years, we've seen a huge jump in the United States, at least, in polypropylene collection. And that's really come down to better sorting equipment. There's been a big shift from having people have to stand on conveyor belts and manually pick things out to using cameras that can tell different kinds of plastic apart and then send one kind one way and another kind another way. And that has meant that it's suddenly worth the cost of sorting out polypropylene when it wasn't a decade ago.
So what year exactly, Robert, did you start? And then what year did you have that eureka moment that where you're into something that's really a great idea?
Yeah, the eureka moment was back in 2018 when Ryan and I were both postdocs at Argonne National Lab. And um, we started the company 4 years later in 2022. So it took a little bit of additional work to try to figure out the nuts and bolts of, well, how well does this technology work and what is it really good for before we decided to take the jump into trying to start a company to spin it out.
What do you have to do to get the technology out of the lab? You actually have who owns the patent to this technology? Does Argon own it, or you and Ryan own it?
The representative for this patents is Argonne National Lab, and we have an option for the Argonne patents.
So you said 2018, and then 4 years. That brings you to 2022, just kind of towards the end of the pandemic. So it's now 2025. Where are you at this stage of eternal upcycling?
I mean, We're still at the lab scale. We're still working on producing liter scale batches of base oils, but really what it's been is kind of an evolution of how do we make this process more efficient? How do we understand how to make the process go faster, the products be a higher quality, really work toward getting products that are sort of to expectation on spec, that they're hitting the VIs, hitting the NOAC volatility, hitting the pour points that a customer would expect for these kinds of base oils. And once we've kind of figured those things out, then it's working on building out a pilot plant so we can demonstrate end to end what this whole process looks like.
How many more years do you think it'd take for you to get to the pilot plant stage?
We're thinking 2 to 3 years. A bit of that is really that um, we kind of need to optimize which product we're working on and also which plastic feedstock we're going to be working with. Because, as we said, like you have to find a plastic that you can buy enough of, and you need to make really certain that you can get it clean enough to go all the way through your process. And frankly, having looked at a lot of other chemical recycling processes that are out there in the market, the big cost factor at the end of the day for most of them is actually cleaning the plastic to a level that lets them run it through the chemical recycling process. So if we can't sort of figure that piece of the puzzle out, it doesn't matter how well the like really cool technology we've come up with works. It's not cost effective.
Yeah. So there's, of course, a lot of projects globally. For example, some of the things that come to my mind, there's a Plastic Waste Coalition. Do you work with organizations like that? Do you get funding from them? How do you get funding since your postdoc ended with Argonne?
Yeah, so we've been primarily supported by the Department of Energy. We won a fellowship from the EERE office called Chain Reaction Innovations Fellowship. It's part of a program that the Department of Energy runs called the Lab Embedded Entrepreneurship Program. So there's 4 national labs, including Argonne, that every year bring in between 2 and 5 startup founders to work at the lab. They work for themselves, but they get to use the lab space at a national lab to move their technology along faster. And it's like really kind of a game changer for a lot of the companies that work in there. So, I mean, for instance, there's I believe it's Clear Flame that was in one of the first cohorts at CRI. They're working on making effectively a like alternate fuel engine for diesel trucks. So instead of running diesel, you'd run ethanol or some other alternate fuel, and that leads to energy and cost and carbon footprint savings. And they were only able to get that technology off the ground because they were able to get into this fellowship program. And so that's basically what it's been doing for us is this. We really wouldn't have started a company if we hadn't gotten this support from the Department of Energy.
And I assume that's a multi-year funding. Is it, Robert?
Yes, yes, yes. In fact, we're still working with support from the Chain Reaction Innovations program.
Yeah. So I don't know much about um, how you bring a startup and bring it to market, but I'm sure you've done a lot of research on this topic. How long would it take to from pilot to get to become commercial to actually get the funding from a venture capitalist, maybe, or do what do they call it? financing. Um, what's the terminology they use in the financial industry? Um, Raising capital.
Well, raising capital is a continuous process. I mean, a startup will usually raise funds four or maybe even more times over the lifetime from going from idea to a um, full scale enterprise, whether that's something that goes public or whether that's something that gets bought by a larger company. So it's sort of you do it in stages. You are kind of setting goals for yourself of I'm going to get the technology this much further along. I'm going to get us this much closer to that ideal goal in the distance. And I'm going to ask for funds from VCs to help support getting to that milestone, something that's going to make the company more valuable, something that is going to get us closer to actually selling products. And ideally, we'll be selling products along the way. So I think one of the things that I'm kind of looking for is, well, there's a lot of base oils out there. Are there applications? Are there cuts of base oils that would be both really valuable and also used in applications where I might be able to sell them to a customer at smaller volumes so that I could actually feasibly be selling products at, say, like the drum size instead of rail cars or cargo ships worth. Because it is going to be 7, 10 years to getting to that large commercial plant, but it might be possible to be selling something at a smaller scale sooner.
So, how much feedstock do you need to produce a drum of PAO?
Well, so we are sitting at around 90% efficiency of plastic in to base oil out. So the like take a drum, fill it up with plastic, and then heap a little bit more on top of it, and that's about how much you'd need to feed in to get that drum.
We were talking before this podcast about competing technologies. What are the other competing technologies out there, as far as you know?
Well, I mean, so you already mentioned the biggest one, which is pyrolysis, and I mean the big thing with pyrolysis is it's a very simple idea. You just heat up something that's hydrocarbon rich, well, whether it's plastic, whether it's biomass, in a space where there's no oxygen, so it can't burn. So instead of burning, it breaks down into smaller and smaller and smaller molecules. And so if that gets down to something that's small enough and useful enough that you can feed it into some other chemical process, then you've got a product. Um, Now, the downside of pyrolysis is it's often very high temperature, very high energy. And also, it tends to produce a lot of aromatics. It tends to produce a lot of char that sort of traps some of that carbon into pretty low value chemicals. I mean, mechanical recycling is also really a competing technology, and I think we always have to be aware that if there's plastic that is clean enough and well sorted enough, that um, mechanical recycling is always one of the most energy saving options for recycling plastic. Um, for polyolefins, there's most of the other chemical recycling technologies are pretty similar to pyrolysis or us. So I mean, you might do pyrolysis where it's just heat. You might do some kind of hydrocracking or hydrogenolysis process like what we're doing. Sort of in between the chemical recycling pie and the mechanical recycling, there's also companies like PureCycle that are using, um, I guess you'd say, solvent washing processes. So they're not like changing the plastic and they're not just like grinding it up and molding it into something new. What they're doing is that they're heating up the plastic in a, in this case, supercritical solvent, and that is washing on a chemical level all of the additives out of the plastic. And so at the end, you've got a feed that is pure, clean polypropylene, and all of the additives, all of the other contaminants that were in there have gone out with the solvent wash. And so you can just keep using that polypropylene over and over again.
So I guess, Robert, two questions from what you just said. Number one, all these alternatives you mentioned, are they feedstock agnostic? And then number two, what would their output be? Are they high value output like PAO?
I would say Pure Cycle is making a high value output. I mean, virgin polyethylene and polypropylene can sell for pretty similar prices to PAO. Um, Definitely much higher than fuel products. Are mostly making feedstocks that would go into making fuel products. So their outputs are pretty low value if you were to just dollars and cents them against the petroleum product that they're replacing.
So how convinced are you that you can bring this technology to commercial, I don't know, maybe 5, 7 years or 10 years from now?
I mean, at the moment, I'm pretty convinced, which is why I'm still doing it.
Well, yes, that's good. Um, well, I guess every time you pitch to a potential investor, right? They would be looking at demand. What is the demand for this product? And then what is the supply, the current supply for this product? So maybe you can address these two things for our viewers in case there's a venture capitalist out there looking for just an opportunity that you're offering uh, to the world.
I mean, there's a lot of base oil out there. I mean, there's a lot of um, less and less every year, but there's a lot of Group 1 capacity. There's a lot of Group 2 capacity. But when you start getting up to Group 3 and PAO, so Group 4, there's less and less capacity, but also those are the grades that we're going to be needing more and more in the next 5, 10, 20, 50 years because those very oxidatively stable, very high viscosity index base oils are going to be what we need for making the world more efficient, for like energy efficiency, fuel savings, longer equipment lifetime. And there's definitely, like, if you're looking at demand growth, the demand growth is for Group 3 and Group 4. And that's kind of where the opportunity lies. And those are the products that we can compete with. There's definitely going to be shifts in the lubricant industry as there's more electrification of personal vehicles. But by no means does that mean that lubricants are going away. EVs still have lubricants in them. Um, they might be fill for life, but they're still critical to making those electric vehicles move. And frankly, they have to be very high performance fluids to be able to support the motors, the transmissions, and cooling the batteries. So again, you're using Group 3 and Group 4s. Um, and like personal vehicles is only a portion, maybe a third, maybe up to half of all lubricant demand. There's still all of the like in commercial transportation, and there's all of the industrial manufacturing that happens, and that's not going away. We're still going to need trucks on the road, trains, cargo ships. We're still going to need all of those metalworking facilities, stamping plants, and there's going to be like a huge demand for lubricants in the long term. And anything we can do to make all of those things more efficient with higher grade base oils, making higher quality lubricants, is going to make a big difference in making the world a better place.
So, Robert, if you can make a PAO with a fraction of a carbon footprint of a typical PAO, how much do you think the market will value that in terms of giving you a premium price?
I would say whether or not we can demand a premium price, I think that we can be at price parity in our manufacturing costs, not just with Group 4 PAOs, but also with Group 3s. So we may even be able to undercut PAOs.
Oh, wow. That seems like a big opportunity for a future investor in your company, Robert.
I certainly hope
The
so.
best, yes, best of luck to you and Ryan. And thank you, Robert, for joining us today and sharing with us your expertise in this area. It's certainly a very interesting area. There's a lot of things going on here. And I don't think we've even seen half of the possibilities that people like you, scientists, researchers, are doing to help our world become a better place. Thank you so much.
Thank you.
Have a great day. Bye bye.